Today's speaker is Dr. Robin Rogers from the University of Alabama. He's a distinguished research professor as well as the director of the Center for Green Manufacturing at the University of Alabama, where he holds both his bachelor's as well as his PhD degrees. Renowned in the field of ionic liquids, Professor Rogers received the 2005 Presidential Green Chemistry Challenge Award for his work in utilizing ionic liquids for the application of dissolving and processing cellulose, and will be receiving the 2011 award from the ACS Separation Science and Technology Division for his work in utilizing ionic liquids for liquid-liquid separation. With that, I'd like to have you all join me in welcoming Professor Rogers for speaking here today. You got it.
Thank you, Chris. It's quite a pleasure to be able to come and talk to y'all today. I grew up in Alabama, and as a scientist, have always held Berkeley in very high esteem. It's always a pleasure to come and visit. And I have to tell you that my talk with all of the students and staff that I talked with today made me understand why Berkeley is so good. And I really appreciate all of the interactions and talks. And I hope that today I'm not going to be bringing coals to Newcastle, but talking to you about my impressions of ionic liquids and what we're trying to do. Having talked to you, I wish I could change my talk and just forget about the slides and just have this one-on-one interaction with question and answer, and maybe after the talk we might want to engage in some of that. But what I'd like to do today is tell you a little bit about my home, which I'm very proud of, a little bit about green chemistry, very little, ionic liquids and green, cellulose and biomass, and then the why or how or whether we go forward from here. Being from California, you may not know where Alabama is in the world picture right here. Actually, Tuscaloosa is located in the central part. All the BP people here should remember that Alabama reaches about that far away from the Gulf. It's a very traditional southern campus. This is a building that was saved from the War of Northern Aggression. And it's a football school, in case you hadn't noticed. This part of the stadium has been expanded, and I was sitting in this blank section Saturday night watching Alabama march on. But I want to tell you that it's more than a football school. The University of Alabama increased its enrollment by over a third, over 10,000 more students in the last 5 years. It's now over 30,000 students. We have a brand new science building, science and engineering complex. It's Shelby Hall, a 5-sided building, a new engineering complex. This building is now gone. They're building a new engineering building here, and all of these buildings are going to be replaced. And so we're finding about $100 million in new building. We survived a lot of this recession because we grew so fast. Maintaining quality, we would maintain, but we had the tuition from out-of-state tuition to kind of impact to save us. So we actually have faculty raises. We're hiring new faculty. We're putting in new facilities. We have more and more students. We think our science is going up. And in the latest NRC rankings, we didn't quite reach Berkeley, but if you check us out, we're not so bad as a department. We also do things that I've seen here in the Institute, which I'm interested in. It's the idea of entrepreneurship. All of my students and staff interact with the Alabama Innovation and Mentoring of Entrepreneurship Center. They've all written business plans. They've tried to see how their science and technology would be applied to the real world. And it's paying off. We've started companies. We're starting to develop new technology. We started the Center for Green Manufacturing in 1998 to do the types of things that you're now able to do very well here. Interact with scientists, engineers, and business people to develop new technologies, to take fundamental science, really understand it, and to apply that science in new and sustainable technologies. This is the team, and I wanted to make sure I put them up there because I'll end a different way. So right now there's 4 or 5 graduate students, a couple more coming. 2 or 3 of the undergraduates have decided that they want to stay and work in ionic liquids. We now have 5 postdocs and a variety of different funding. Okay, so I'm not going to spend all day trying to convince you what an ionic liquid is, although I should spend all day trying to convince you that maybe most of what you think an ionic liquid is not true. Now I would say y'all probably know the answers to that, so I would say the rest of the world, most of what they think an ionic liquid is not true. Think about a class of materials that are defined by a melting point. A salt, which melts below 100 degrees. How many different materials do you think might fit that classification? And I can guarantee you that there's probably not a single property, other than being a salt and having a low melting point, that is true of every member of a class of materials that are now being called ionic liquids. But people were excited about these things because they are liquid. So it's a salt. Now it's not so novel today. When I started working on this 10 or 15 years ago, a salt which was liquid at room temperature, this is water, this is an ionic liquid, that could be used as a solvent, that wouldn't evaporate or burn, that's ethanol, which y'all are trying to make, and this is an ionic liquid, had no vapor pressure. And in some cases, and this is actually why I won the Separation Science Award, Technology Award, in some cases, ionic liquids are immiscible with water, allowing you to do separation. So there's no wonder that people got excited once they learned about this class of materials. Say, wow, a class of materials that have all those properties would be amazing. But I will emphasize now and again throughout the talk, all ionic liquids do not have all those properties. Just to give you a little bit of history, and don't fall asleep during this part, I just want to mention some names, and since this is being taped, if you want the references, you can go back. The first philosophy that I would call of ionic liquids painted this picture of organic salts with inorganic anions that melted at low temperatures around 100 degrees, and most of the things that were done by inorganic chemists who were familiar with high temperature molten salts. And there's been some work that you may not have put under the category of ionic liquids. Frank Hurley and Thomas Weir at Rice University looked at electro deposition of aluminum from low temperature or ambient temperature molten salts. Certainly Bob Osteryoung and Bernie Gilbert did a lot of work with room temperature molten salts, some very good chemistry, and notice this is all back in the 70s. And then a friend of mine, John Wilkes at the Air Force Academy, is probably one of the premier early pioneers of the field of ionic liquids. And this is Chuck Hussey, who's now, he was chair at the Department of Chemistry at the University of Mississippi. And they started using the dialkyl imidazolium chloroaluminate melts for electrochemistry. And John actually designed that, made that a purposeful choice, because he looked at the HOMO-LUMO gap of the imidazolium ion and said, this should be fairly stable for electrochemistry. Now there's a connection with the University of Alabama that most people don't know. Mike Zawaratko and I graduated from Jerry Atwood's group at Alabama at the same time, 1982. Mike went to work with John Wilkes at the Air Force Academy to work on these room temperature molten salts. And they published a communication in 1992 on air and water stable ionic liquids. And that was really one of the keys. Nobody would think about doing organic chemistry on an industrial scale for all the things we've seen in aluminum chloride melts. But if you had a liquid salt that you could pull out of a bottle and pour it into your beaker, all of a sudden things changed. Now there are a lot more histories. I like the ones that John has put together. And if you're interested in any of those, I can point you to the literature. So we're now in the mid-90s. Ken Seddon moved to Queen's University Ionic Liquid Laboratory and started doing his super secret work in ionic liquids and developing all this solvent chemistry. And then most of you know there was a big article in the mid-90s in Chemical and Engineering News that Mike Fremantle started reporting, and then all of a sudden everybody started getting interested. And most of the work developed around these ions. And that's why people still have an impression that ionic liquids are only one type of material. The imidazolium ions that John Wilkes started developing, the pyridiniums, and then quats and phosphoniums. I know Professor Prausnitz knows that many of these compounds for liquid ion exchangers have been around for years, but they just weren't looked at as solvents. They were liquid salts, though, that fit the definition. The anions were limited to inorganic anions. You could tune things, but they were again said to be no vapor pressure, non-flammable, green, sustainable. And then with all these publications, everybody started going back in the literature and trying to find everything that would fit that definition. And they found this article by von Walden in hindsight, where he made ethyl ammonium nitrate that had a melting point of 12 degrees. And then Ken and others said, this is the first example of an ionic liquid, and now you're seeing thousands of papers which report that fact. I would argue that that's not true. This is a salt which meets the definition of an ionic liquid. It doesn't meet the strict definition of composed only of ions, because as chemists we know there's going to be an equilibrium in there. But it can no way fit this change of thinking that came about by looking at ionic liquids as solvents. So don't let anybody tell you that your work was predated by thousands of other people. What you're doing today is extremely important. It is new science. And then it actually gained a lot of attention because of this whole connection with green chemistry. So where did that come from? Well, Paul Anastas and John Warner, who are getting all types of attention now, wrote a book on the principles of green chemistry, and one of them was essentially to get rid of solvents. Or if you can't get rid of noxious VOCs, make something safer. Well, the most prevalent route to chemicals getting into the environment was through the air and through volatilization. So if you remove that, certainly it's safer and greener. So I asked Ken if we could put together a NATO meeting, if he'd go in on a NATO meeting, and we did in the year 2000 in Crete in April on the beach, because I got to choose the location. And believe it or not, at this meeting it was difficult in the year 2000 to get 50 people worldwide, all expenses paid, to go to Crete to talk about ionic liquids, because there simply were not that many people working in the field. This is Ken. You know, I'm not wearing my red jacket here because it was lost. My luggage actually was lost on the way to this trip. I kind of regret that. But people you recognize, like Tom Welton, and I saw Jim Davis he's hiding. He's kind of short. There he is. Jim Davis, Peter Wasserscheid, Luke Mons. Actually, I had a couple of graduate students who got their picture in C&E News because of this. But a lot of names that you would recognize. And in the book, the results came out. There were 11 outcomes. I'm not going to bore you with all of them. But this is very important for people who work in the field of ionic liquids. The first outcome decided by this group of people in a strategy session to move a field forward was ionic liquids are intrinsically interesting and worthy of study for advancing science. The use of ionic versus molecular solvents with the expectation that something useful may be derived. We were after scientific advancement. But notice the second one, because I wrote that one. Combined with green chemistry, a new paradigm in thinking about synthesis in general, ionic liquids provide an opportunity for science, engineering, and business to work together from the beginning of the field's development. There was not one thing that said ionic liquids were green. Not one. It was an admonition. If you're going to work in a new field, be sustainable. Make sure that it fits environmental goals. But most of you know that that's not really what happened. People started hyping these as green solvents. 1 year later, exactly 1 year later in San Diego, I organized a symposium at the ACS meeting, and 350 people showed up on the first day. 1 year after I could barely get 50 people paid to go to Crete, 350 people paid for themselves to go to San Diego. Now, I like San Diego, but it's not Crete. And then this was just replicated. Books have come out, international congresses. In fact, the next international congress is going to be in Washington, D.C. in June. Publications started pouring out. There's been like 20,000 since that time. Why? I think this change in thinking is what's important. You need to think like a chemist or a chemical engineer and change the way that you think. I like this quote. The important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. Well, if Paul Walden was working with ionic liquids in 1914, why didn't he dissolve cellulose? Because it wasn't in the thought process. And it took a long time to get into the thought process, and a lot of people working in the area to bring it there. Now, those of you who had to come up to speed on ionic liquids know the challenge you face in terms of publications. Here's the NATO meeting, and then the growth. I think this is total growth, and not annual, but total growth in publications. This was done in April of 2009. So 2009 ended here. 2010 is still going up. I think the current number is very close to 20,000 publications since the NATO meeting in 2000. Worldwide interest. Not all of those publications are good, by the way. What I found fascinating is as people learned about ionic liquids in different fields, it started with inorganic chemists, it moved to organic chemists, then it moved to physicists, and then it moved to a variety of different fields, then the number of applications just kept going up. And I think today you can do a SciFinder search and you can try and determine applications, and we're not going to do it by hand. You're welcome to do it. But there were roughly 3,000 different types of applications, the way that you could categorize these materials. So that was then. This idea that they were solvents with little or no vapor pressure and that you could tune them. I bet y'all still put that in your proposals today. You can mix and match the cations and anions to give you the physical properties that you need or the engineering properties that you need for a particular application. That's still the promise. It is also the curse of this particular field for those of you that are actually trying to do that. But again, not all ionic liquids have these properties. And that led to a paper that we like to do a little myth busting every once in a while. They're really simple papers. We were actually being funded by the Air Force to develop ionic liquid propellants. Actually, we still are. And we published a simple little paper that said, hey, if you think all ionic liquids are non-toxic, non-flammable, et cetera, you should be careful. I was getting phone calls from high school teachers who wanted to use butylmethylamidazole and PF6 in their high school classrooms for liquid-liquid separations because it was green and they wouldn't have to use an organic solvent. And I was still looking at this white smoke that was coming up in our hoods when we were doing those experiments and saying, they're going to kill somebody. If you suspend your belief as a chemist and just accept the press. So one myth buster was this one. These become highly cited papers. It's amazing. You should try it. One was this. The other one was BMIM PF6, where we isolated the fluoride and said, I'm an inorganic chemist. If you put PF6 in water, you know what's going to happen. And it did. People still do it. Nonetheless, it led to a problem with overgeneralizations. And that's really where we stand today. So we have this Nature paper that came out in 2005, warning shot for green chemistry. Solvents with an environmentally friendly reputation may kill fish. And they cited an article where one ionic liquid was put into water and it killed fish, of course. But you look at the composition of the ions, and I told people for years and years, if you want a poison, I can make you one. It's easy. In fact, I don't want to tell Homeland Defense because there are a lot of ways to use these that we don't want people to know about. But anyway, the idea here is that I had to finally put this in terms that any chemist would understand. And it's like, How many of you would allow this statement? Benzene is carcinogenic, therefore all solvents are carcinogenic. How many of you would allow that to be published in JACS? Then why do you allow it to be one ionic liquid is carcinogenic, ionic liquids are carcinogenic to be published in JACS? On the other hand, the hype is all over the place, and I can tell you, if you write a paper and you write in the introduction something that sounds like water is green, therefore all solvents are green, I won't read any further. I send it back, reject, because it's obvious that you don't know anything about the field. So you can't generalize like that. This has really been held back, and those of you who have been faced with this criticism of your papers or your work, hang in there. It's not true for what you're doing. On the other hand, don't ever fall into the trap of trying to promote your work under that category, because it's equally dishonest. But let's go to something that y'all are doing. It's another principle of green chemistry. A raw material or feedstock should be renewable rather than depleting whenever technically and economically practical. This actually led us into the field of cellulose. Now, this current biorefinery process is interesting to me, but I still find it kind of fascinating that cellulose is the only active contributor that people keep promoting. Sure, there are plenty of cellulose sources. We're from Alabama, so we prefer trees actually over grasses and canes. And there is certainly the motivation for why cellulose is important. All right, so now I get to teach at Berkeley. I want to see how many of you can answer this question. It's been asked all around the world. How much time does nature need to produce the amount of cellulose equal to the annual tonnage of the world's entire chemical industry? Every chemical made around the world for a year in tons. How much? Oh, you want multiple choice. Okay. You got a choice. 7 minutes, 2 days, 6 weeks, 3 months. I know who the A students are now. 2 days, but think about that. 2 days. Nature's doing a heck of a job. And what I keep trying to tell people when I show this slide, that's only one of nature's polymers. Only one. We don't use this material at all. If you look at 40 times 10 to the 9th tons per annum of yearly generation of cellulose, we use a very small fraction as a raw material. Of that, most of it is pulp, a few natural fibers, and then for chemicals, only a small fraction of that. Can we change this picture? This rush to bioethanol, which is an attempt to utilize cellulose, is forgetting about lignin. It's forgetting about hemicelluloses. It's forgetting about waxes and extractives. And all of these can add value to a true biorefinery process. But what's the challenge in a biorefinery? Y'all should probably give me the answer to this. I can just tell you from my perspective, there's no common technological platform. You're using a grass from Illinois. Now, you're in California. I'm not sure I understand that. But you're using a grass from Illinois. I'm using trees. The technologies, if you're going to treat that stuff directly in what we're trying to do, is not going to be the same. And in fact, your grass is going to change depending on whether they had a drought that year or too much rain or the sun. How is that going to affect your process? Or can you engineer that? What if we could get a better separation of just the biomass components and try to work our technology platform on the component polymers rather than on the biomass itself? So DOE has this grand plan, and we're all working in this area. Biomass feedstocks, they got that part. They know thousands and thousands of products that can be made, but it seems like this middle part is always, and a miracle happened. This is really that's really the problem, isn't it? How do we do this without using more energy than we're going to get out in the entire process? Well, I consider the real challenge, and it is a DOE grand challenge, to be able to dissolve any lignocellulosic biomass and to easily and cleanly separate at least the three major components, as well as taking advantage of extractives and other materials that might be there. So why are ionic liquids relevant to this? I'm not a big fan of using ionic liquids as solvent replacements. I mean, if you got something that works, it's non-toxic, low energy, why do you want to use an ionic liquid? There has to be a good reason. However, if you can find something that an ionic liquid can do that nothing else can do, or virtually nothing else, that might be something worth looking at. So you have to look at the fact that ionic liquids can be amazing solvents. One ionic liquid, the first one that we looked at, butyl methyl imidazolium chloride, will dissolve incredibly hydrophobic materials. CMPO was developed for nuclear extractions. It was developed to be totally insoluble in water. It can dissolve cellulose, but the ionic liquid itself is totally soluble in water. When water is in the ionic liquid, it won't dissolve these things. And of course, that's where the process actually came from. So one of the original studies that we did, this is Wattman filter paper, and there's really no truth to the rumor that's how we discovered this. Y'all must be asleep not to laugh at that. But that was real time. Real-time dissolution. This was heated a bit. You saw a little water being given off as steam. Real-time dissolution and reconstitution simply by dumping it in water. Or if you wanted to extrude it in water or find a fancy way to make beads, you can control the coagulation. So we were excited about that. It took us a long time to get our sponsor excited about it enough to actually try to patent this, which we couldn't understand. But it led to then this whole idea of materials from biomass. You can dissolve cellulose, you can make things. You can dissolve cellulose with other polymers. You can dissolve cellulose with nanoparticulate additives or with proteins. You can make fibers, beads, or membranes. You can make chemical sensors. We've made functional textiles, drug delivery agents. This was a NOx detector, I think it was NOx detector. We've made active cellulose supports for supporting cells or membranes. And that was the sort of the story around 2005. And this won the Presidential Green Chemistry Challenge Award, not because it was an ionic liquid, but because it was a platform that had the potential to replace some of our reliance on oil because of new materials. It wasn't a biofuel or even a biorefinery. It was a materials award. I'm not going to go into a lot about how it works, but I will say that as scientists, we did want to know. And in our initial studies, which were published in 2006 with Guillermo Moyna, it became very clear that our hypothesis was correct. The chloride was going in, and it had no good hydrogen bond donors to interact with in the ionic liquid. But of course, in cellulose, it went right after the hydroxyl groups. Very strong interactions. It not depolymerized, it dissolved the cellulose. And we know it's a dissolution, not a degradation. We can degrade it, but the initial studies were dissolution and degradation. And we published this paper, and then of course people started looking at a whole variety of different anions that would do this. They also played with the cation, and the role of the cation is still very important and an unanswered question, which I believe some of y'all are working on as well. Keep at it. It's a very important question. Not every anion will work. Now, I will tell you, if you try an anion with a hydrogen bond donor, my first inclination will be that won't work, like choline, because it'll interfere with the anion's ability to interact with the cellulose. But why would not some big tetrahexyl or dodecyl ammonium, why won't that work? Why does it look like the cation has to be only of a certain size? The acetate, formate, phosphonate, amino acids, all of these that have been used to dissolve cellulose have this ability to interact with the hydroxyl groups and disrupt the hydrogen bonding. A lot of different types of biomass were dissolved: cellulose, lignin, chitin. I don't have time, but we just published a paper, and we're actually starting a company because we can use an ionic liquid to extract in one step high molecular weight pure chitin from shrimp shells in a higher molecular weight than has ever been observed before, and we can make fibers out of them directly. Those are the things where you would want to go after an ionic liquid approach. All right. So now let's come to work which is more related to some of the things that y'all are doing here. We're back to this biorefinery concept, and I want to emphasize again that if the oil industry, if BP had to rely on only gasoline, I don't think they would be profitable. An oil industry takes a barrel of oil and makes thousands of products, and I think that should be the goal. Thousands of products from the ability to take the biomass and dissolve it. Now, if you were to take lignocellulosic biomass and you were able, with a one-step process, to selectively get these three components from any biomass, imagine what you could do. You'd have a polymer that would be a lot more consistent biomass to biomass than the biomass itself. So if you could process the cellulose, hemicellulose, and lignin, sure, you can make fuels if you want. But I'm thinking chemical feedstocks, but more importantly, the polymers themselves that nature has already made can be easily manipulated in the solution state to give us thousands of new products and materials. So this idea is not new, of course. There's been a lot of pulping technologies, and I use that terminology on purpose. Let's think about pulping. And again, Alabama has, in the past, had the world's largest pulping operations. What does pulping do? Its sole goal is to get lignin-free cellulose from the biomass. It doesn't care about the cellulose, so it tends to degrade it. It's a chemical process. It's about 50% efficient in delignification, and the bleaching is followed, which tries to destroy more of the lignin. It's a dirty process. And we've tried organosolv. I'm not sure why organosolv never caught on, except maybe the pressures and some of the temperatures that were involved. And then mechanical pulping, which also requires energy. The difference between what we're doing and any of these processes is that we can dissolve the cellulose. We can dissolve all of the biomass. So this pulping was never a dissolution of cellulose. It was a removal of the lignin. And that's an important distinction. But let's say that we use their terminology. Let's say pulp yield is the amount of biomass that you get back from your process. And lignin content is the driver. You're trying to get zero and as much of the biomass. There might be 60% carbohydrates or so in the wood. And craft pulping usually gets you somewhere in that region. So let's see what we can do with ionic liquids. Our first paper was published here about 2006, and it really, again, was, we like to do simple experiments. I love simple experiments. We just tried to dissolve wood, and it worked. And we followed it by NMR, and in a more complete study, which was just published last year in Green Chemistry, we showed that you could get complete dissolution of pine and oak, by the way. We use southern yellow pine. By using an ionic liquid, you could get everything into solution, and what you recovered was a cellulose-rich material. You can see the color, so you know it's not all cellulose. Well, I'm going to call that the pulp, and you get pure lignin. That I thought was, always thought was pretty interesting. And we started thinking about this, then automatically started thinking about this now as a separations problem, because I started in the field in separations. You've got these three major biopolymers. Are they all soluble in the ionic liquid? The answer is yes. We looked at microcrystalline cellulose. We used xylan as a hemicellulose surrogate. We used a kraft pulp lignin for our lignin surrogate. And we found that very high solubilities of all of these components in the ionic liquids that we were using. And then we said, okay, we do a survey of the solubility of these in a variety of different solvents. Some of this can be found in the literature, some we did, or this is our data actually. And we found things like if you use 1-to-1 acetone water, the cellulose, of course, is not going to be soluble. The xylan's not soluble, but the lignin's pretty soluble. And then if you use 1 weight percent KOH, you can get solubility of the hemicellulose and not the cellulose. So if you first coagulated into this solution and recovered the hemicellulose and lignin, and then you use this solution and got the inulin AT, you could even evaporate the acetone and recover the lignin. So there's a separation process there somewhere just by looking at all of the various solubilities of these materials. I'm going to skip over this one. So in the paper that we published last year, we took wood chips, ground it a little bit. I think I saw your grinding stuff, which is very elegant downstairs. I think we were going with the wood chips around 0.12. It's still pretty low for a commercial process. And then we would cook it with the ionic liquid, and we would get a solution. We would then filter it and regenerate it with the acetone water solution, and we'd get a carbohydrate-rich material. In this case, we were trying to get both the cellulose and the hemicellulose. Then we'd get lignin in the solution, evaporate the acetone, precipitate the lignin, and then we could recycle. And you can recycle these materials. In the mass balance, we're not in good shape yet. No, we're definitely not in good shape yet because we still have quite a bit of loss. But if we look, I'll try to put this in a better form. If we look at what we are accomplishing in this one first step process, with the ionic liquid process, we're getting a pulp yield of about 50% with a lignin content of below 25%. Not quite into the pulp region, but that's our first experiment. That's like the first try. We started thinking about how could we improve this. I know that's pretty fast, but that's a whole paper. I want to get into some of the newer stuff, which may be of interest to what y'all are doing here. It's not good enough, but it was pretty interesting. You can get a pure lignin fraction. You can get 20, 30, 40, 50% delignification in one step. But thinking like a chemist, how could we improve that? And we started looking at trying to catalytically cleave the lignin carbohydrate linkages. Now, the covalent linkage is the problem because remember, I've already shown that if you just had lignin, hemicellulose and cellulose, they'll all dissolve, you can separate them. But nature's not quite like that. You've got this bond, covalent bond, that you have to worry about. So what if, as a chemist, I could find a catalyst that would just cleave all of the ether bonds holding the lignin to the hemicellulose? If I could do that, wouldn't I then be able to separate all of the components? So we decided to look at polyoxometallates. I think it's Craig Hill in a neighboring university, Emory, had looked at palms for bleaching purposes for a long time. And I visited maybe 10 years ago. And they were talking about how you can use the palm to completely oxidize all of the lignin to essentially air and water, which I thought was good. But what I wanted to do was to be able to use the palm to just clip it. I didn't want to destroy the lignin, but I knew that it had reactivity with lignin. So if we did this properly, could we just snip it? Was there some way to, get it cleaved where we wanted to? And this is the picture I'm using. So could we use the palm to cut that bond in this dissolution? That's Hector's picture right there, by the way. Hector, yeah, that's your picture, that one. So to clip this, so that you can then separate and get everything that you want out of there. So let's take a look. The only difference between what I showed you and this is that we're adding a small amount, I think it was 1% or less, maybe, no, it was 0.5% and even less of a polyoxometallate right at the beginning. And what we found is, holy smokes, you could reduce the dissolution time from total dissolution that might take 46 hours. All of a sudden it was only 15 hours. Now that's still a long time, but think about how much time you've cut just by adding a little bit of a palm. Without the palm, 94% of the pine in this region could be dissolved in the ionic liquid, but if you add 0.5%, all of it dissolved under those same conditions. So there was no doubt something was going on with the palm. And we started looking, and I apologize for the graphs. There's no other way to get across all the data. So you see a lot of these. This is the pulp, and the white part is the carbohydrate, and the upper part is the lignin. This little fraction then would be this little fraction would be the loss of lignin, and this would be the lignin yield right here. So I'm going to just focus on these numbers. With no palm, this is the pulp and lignin content I showed you before. But notice when you add a little bit of palm, you get an increase in your yield of the cellulose and a decrease in the lignin content. And I think that has to do with the fact because we don't have to so aggressively heat it for such a long period of time, we reduce the degradation of the cellulose, allowing us to recover more. But we're also separating or getting better delignification. And look at the 0.2%. Wow, we're all the way up here with much lower lignin content. But then look at what happens to the loss of lignin here, 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 and here. So it's pretty obvious that we're doing what we want to do just a little bit too well. We are clipping the lignin, but we can't stop it yet so that it decreases the amount. This can also be seen if you look at this instead of looking at the pulp. You look at this with respect to each individual biopolymer. So you're recovering with no palm close to 60% of the carbohydrate. But if you use 0.2% palm, you're getting up to almost 70% recovery of the carbohydrate. And the loss of lignin from here to here to here. You can see exactly that we are attacking the palm, and the secret behind these regeneration schemes is that the way we do things so far, if you get the molecular weight too low, you're going to lose it, and you're not going to recover it under the scheme that you're using. You can eventually get it out through other mechanisms, but under these conditions that we're using, you're going to lose it. We can also recycle the ionic liquid, and for those of you that think ionic liquids have to be perfectly pure and no water and nothing else in there in order to work, this one was black. Many of you worked with lignin before. Had all sorts of stuff in it. All we did is evaporate as much of the water as we could. It increased the efficiency, and I think that has to do something with the solubility that we just saturated the solution. But we increased the efficiency, and with the palm, we also increased the amount that we recovered. But notice with the palm case, we decreased the efficiency of the delignification. I'm looking at the ratio of the black and the white. Now, why might that be the case? I'm going to skip over the others. Let's look at this, and then I'll tell you my theory on that. This is the Kraft pulping region. This is the first paper we published. And now these are all the other results that we've tried. And I want you to notice that we're actually doing at least as good as Kraft. And I think that we can do better. This is not bad. This one's not bad. I'd like to see the lignin content come down a little bit. These results were with a different form of palm that was so active it actually degraded the cellulose. And I know that's what many of you want to do, so don't give up on that because I'm pretty sure that will work. But just by putting a little palm, look how we were able to move around and sort of control. And whether you like this or not is going to depend on what you want. If you just want a high cellulose pulp with no lignin, this might be one approach that you would take. Now, the FTIR of the recovered lignin, yeah?
You're putting an acid into a really basic solution. What difference is it going to make, really?
What do you call acid and what do you call base? I think this is going to be...
Even acetate is quite basic. And
how do you define basicity in an ionic liquid?
it's going to suck up protons.
From what?
The acid.
What acid?
The one you're adding with this.
Oh, you're talking about the palm. Yeah, so I didn't put that in here. It's in the paper, though. That there was a reaction with the palm, a small reaction to make a small amount of decomposition product, but we were able to actually go back and forth in the redox chemistry in the ionic liquid, and it was stable. So it's a very valid concern, and there is going to be some reaction. But in the bulk of the presentation, I'd like to focus. I was just focusing on how the palm would react. You can change the ionic liquid to change that chemistry as well, but you give up some of the other benefits of using the acetate if you do so. But it is a very important question, the reactivity of the palm with the ionic liquid. That was essentially what you were asking, right?
So acidic palm is not an acid plus palm. It's actually acidic.
It's a palm with about 4 or 5 protons on it.
Okay.
Yeah. In looking at the FTR of the recovered lignin, the only thing I'm pointing out, because it is all we can ever find in there is lignin, is that if you look at the palm, you'll see that it looks like we may have lost some. And in fact, we did an EDS study, a very rough estimation. We might have lost up to 1% of the palm that we added. It's not a huge loss, but that I don't think we'd be able to tolerate that. So we'll have to find a way to keep our catalyst from going in the product. On the other hand, the pulp, the carbohydrate-rich material, both by FTIR and EDS, showed absolutely none of the palm. So we still get the product, the main product that we were looking for. Now, I don't have a lot of time, so I'm going to go through this next part very quickly. Just by changing the conditions of the dissolution, you can dramatically change the chemistry of the extraction of what you want to get out. Let's say instead of using 110 degrees to protect the ionic liquid from degrading, let's say that we go above the glass transition of lignin. And let's go up above, let's say above 150. And if you look at this pine dissolution, 110 degrees, 16 hours, you only get 50% yield. You get 90% of it dissolved. If you do a very short period of time at 185 degrees, then you get mostly residue. But if you do 170 degrees for about 30 minutes, you can actually dissolve about 90% of the material. So the point I'm trying to make is, do you want total dissolution, or can you handle just getting 90% of it in over 5 or 10 minutes or 30 minutes? And you'll find that you get a lot of change. This is under the 110 degrees for 16 hours. This point is 175 degrees for 30 minutes. So you make the choice. Which one is better? This one actually seems better on energy content, but there is some degradation, as you would expect, of the ionic liquid as well. Again, you're talking about tenths of a percent, but in any process, that's really going to add up. I wanted to just mention bagasse as a grass and indicate that we have looked at changing the time and temperature, as I just mentioned. And it does appear using bagasse. This is the tradition, what we call the traditional. Our first conditions, 110 at 16 hours versus 165 at 10 minutes, 175 and 185. Just above the glass transition of lignin, we get a better yield of the carbohydrate and a lower lignin content. So all we did is change the conditions, and we got better, much better result for the purpose we wanted, focusing on the pulp, a low lignin cellulose pulp. So you can also try and go too high. If you go too high, you start degrading the polymers, and that should be pretty obvious as well. All right, I'm going, because of the time here, I'm going to go through this last part pretty quickly. That's probably the most of the data that you need to actually retain related to the biofuels project. But I would like to point out, even with just the biomass, you can make fibers, you can make polymers, you can make materials, just like you can with with cellulose only. There's a whole market for materials like this, byproducts of your process, that you could use and sell to help finance the biofuels part. What I wanted to tell you, because I haven't seen it a lot in papers, you may be working on it here, but I haven't seen it a lot in the biomass field, is that if you use a catalyst to try and help you cleave the lignin from the hemicellulose, you can do a much better job of dissolution and separating the polymers as polymers and making a consistent feedstock. We've only done one. There must be hundreds that you could try to optimize this particular type of process. That's the excitement of the challenge. Palm will enhance the wood dissolution, but not only that, the conditions that you use will enhance your product, depending on which product you want. Going above the glass transition of lignin really seems to help. Lowers the time that you have to do the dissolution, improves the separations. The things that we're doing were derived from the pulping industry. And that's another sort of lesson that we've learned, is that a lot of the techniques that are out there didn't have ionic liquids to try, but the principles that they're using are still just as valid to what we're trying to do. Although I was asked by one reviewer why I wasn't comparing to peroxide or something like that, and I had to explain if you put peroxide in the ionic liquid, as I was asked just a minute ago for palm, then you don't have an ionic liquid anymore. So you do have to be careful. Well, one of the things that we're doing from here, we've started a small company. We won our first SBIR based upon the catalyst separation. We would like to be able to develop a commercial enterprise in developing little plants that you could put anywhere, use any biomass feedstock, have this wet, nasty feedstock ground and put into dry, shippable polymers that could go to any processing plant that you want. And Dr. Garreau got her degree from PhD in organic chemistry from Boardwingo at the University of Alabama and is now the CEO of this company. And I put this up here as another idea to give you that we're not just generating new knowledge and new technologies, we're also generating entrepreneurs, new companies at the University of Alabama. Ionic liquids require you to think. I talked with many of you today, and I know you got sick of me saying the same thing, but I'm a chemist. I started life doing crystallography. I see things at a molecule level, an ionic level, a molecular level. If you look at everything that you're trying to do from the science of how the atoms are interacting or the molecules are interacting, you'll be much better off and have a much better appreciation of what you need to do to make it work. This field is fascinating because everybody thinks it's old. Everybody thinks it's not very important. When I say everybody, I'm not talking about y'all, but you must know the impression of ionic liquid chemistry that's out there as green chemistry. But it's fascinating, elegant, and important science that still needs to be done. We can engineer salts by controlling the functions. And I'm just going to show you a couple of these. I'm going to skip through some of the hype that I put up. It's the selection or choice of the ions which is key. Do you know why there's a difference between bemum chloride and bemum acetate? Do you know why chloride or acetate works differently? Do you understand what happens when acetate goes in water versus chloride? These are all kind of simple chemistry things, but most people working in this field are not applying the freshman chemistry that they learned about this stuff in the way they think about what's happening in their process. I would encourage you to do so. And then look at the function of each of these. Now, if we want a low melting solvent for cellulose, we choose something which is a good hydrogen bond acceptor. We choose something that has no real good hydrogen bond donors, and we put them together, and by and large, everything we've tried dissolves cellulose. On the other hand, what if you want a material that will propel a rocket? You might choose high energy content and oxygen balance, and then all of a sudden you have propellants or energetic materials. Actually, our major funding comes from the Air Force in this area rather than in biomass. But what about biological activity? I told people for years that ionic liquids, I could make a poison into an ionic liquid, and then I had Buzz Q from Pfizer talk to me one day and said, you know, there's an old saying among pharmacists, the difference between a drug and a poison is the dose. And I thought about that and I said, holy smokes, I'm familiar with all the polymorph cases in pharmaceuticals. What if I gave the pharmaceutical industry a liquid salt that could never suffer from polymorphism? And I really got excited about that. We've actually filed a lot of patents in that area, but it's just something different that nobody had yet thought to do that is still pretty simple, using the ionic liquid form as an active pharmaceutical ingredient. And Dr. Rodriguez was actually a part of this work, which I think is going to be very important. We've made things like lidocaine docusate. We just published a paper on liquid aspirin, although nobody understands that liquid aspirin is not aspirin in solution, but aspirin which is in the form of a pure liquid salt. Now you may not want that, but you can certainly make it. A lot of room for a lot of science. You're at the home of big science here. My history as a chemist always reflects on Berkeley, and the amount of effort and the extremely good work that has come from this institution. And you have the funding, the people, and the instrumentation to make a major contribution to society. My only plea to y'all, as a chemist from the University of Alabama, is to think and to make sure you maintain that high science as you try to develop some of these technologies. In the field of ionic liquids, combine what you do with green chemistry and try and make something sustainable. But don't fall into the trap that many other people have done. Let green chemistry guide your work in ionic liquids, not define it. Very, very important distinction. Now you're going to have plenty of opportunities to talk about ionic liquids. Pacifichem, for all of you that can get funding to go to Honolulu near Christmas. But also the most important one will be the International Congress on Ionic Liquids. It'll be held in Washington, D.C. Members of your institute have already been invited to give talks, and I hope that I will see all of you there. It's a fascinating world in ionic liquids. I appreciate all of the elegant work that you're doing here. I look forward to seeing more of it. Good luck. Thank you very much. You know, that's what you get to do with us as a speaker. You know, if you speak past the time, you don't want any questions, you just speak a few minutes past. But I would be happy to answer any questions if you'd like to get into a discussion. I don't know, do people have to go? Or?
People who need to go should feel free to. But
Yeah, I won't be offended.
If you hear the questions, they're certainly welcome to see.
What does the palm happens to? Is that an oxidizer?
Yeah, so the essential chemistry is, and I'm not, to be honest with you, not an expert, but the initial chemistry is an oxidation and reduction. And what I found fascinating is that even though we initially had some palm reaction with the ionic liquid, by heating we could reverse that, and that we could recycle this and we can keep recycling it. So unlike the aqueous system in the ionic liquid system and going through the water and everything else, this is, without even trying, we have been able to reoxidize the palm. So you have the palm, which oxidizes the lignin, but then the palm has to be reoxidized in order to work again. I had some slides on the chemistry. It's basically, as I understand it, a quinone mechanism. But I would prefer not to have to go through and draw it all on the board. Yes?
A challenge for biofuels, which are a really low-cost commodity price driver, is that we're using a catalyst solvent that is recyclable, which means you have to recover it. And in the work that I do, it looks a lot like recovering the ionic liquid from pulp, for instance, is a major challenge to do cost effectively. And anytime you have to rinse out or wash out or recover in some way a liquid from solid, you have this inefficiency.
Yes.
See any solutions to that?
Yes, yes. I have lots of thoughts. I meant yes on the thoughts. I didn't mean yes on necessarily the solutions. BASF licensed our technology to make fibers, and they're in pilot plant production with several companies on making new fibers, textiles. And the biggest challenge is, although they don't really talk to me, it's all super secret, the biggest challenge is the cost of the ionic liquid, which I don't consider to be the challenge, and the recycle, which is the economic barrier. But that depends on the cost of your product, right? What you can get for the product. There are many ways to think about recycling the ionic liquid. One is to use a different solvent. One is to find a way to do it without solvent. So it is a major challenge, and one that we are working on. One that I can't really talk too much about, but certainly everybody recognizes those challenges. Now, one way to get around that is to say, I don't care. I can just boil, I can wash it with thousands of tons of water, and I can just boil off the water. Now, is there a product that might be high enough value to do that? I think I've found one It's not in the lignocellulosic biomass, but it's in the shellfish biomass. I can sell a chitin fiber for $60,000 a gram. Do you think I can afford to boil a little water in order to get it? Of course. So the answer to your question is always going to be, what is the outcome? Now here is where we may differ in opinion, or your sponsor and I may differ in opinion. Is biofuels the appropriate target to be using an ionic liquid approach? And you've essentially asked that question. I don't think so, but it's not my approach. It may be, it could be very viable, but only if you think beyond biofuels and you think about every other product that you could make. In the chemical industry, well, y'all know this better than me. In the chemical industry, you hardly ever start with a commodity. You start with a specialty, and then you develop all your procedures and your scale of manufacture and everything else. So what is the high-value specialty chemical? It's not going to be ethanol. So I forgot to tell y'all this. You know, I told you I was from Alabama. We've been making ethanol out of corn for a long time, but we drink it. You know, we don't try and burn it in our cars. This is an old technology. It's a low value. If I could do this, I could help you go to ethanol by having a feedstock that you did some other depolymerization on. But why is it that you have to do everything in one step? Why is it that you have to dissolve it, make the ethanol? What are you doing with the lignin? You have to worry about the lignin at the same time. Why not separate it? And then, even in a continuous process, separate it and then go into your catalyst. Wouldn't your enzymes work better if the lignin wasn't there? In some cases, I don't know. Nobody wants to give y'all. It's all super secret work, I say. I don't know. Is that any kind of an answer to your question? Seriously, there are a lot of people who are working on this sort of around the world, and I think that the approaches are the ones that I said. Either find a solvent that's cheap enough and easy enough, find an ion exchange mechanism that you think you can use on that scale with all those impurities, or find a way to do it without using a solvent. I think we've got some inroads to the last one.
Just a minor technical question. What was the water content of your ionic liquid once you boiled it all off?
The ionic liquid, I mean, I don't know if y'all have noticed, but the water content in the acetate is not so critical as in the chloride. And so I think you just, with this one was down to like maybe 10% water. And we haven't really optimized. I think that that's really something that could be done. But if if you haven't understood what I was saying about the difference between the chloride and the acetate, it really has to do with the acetate being a buffer and the interaction with water that won't interfere with the dissolution of cellulose. If you have chloride in there and you put water, there's no place for the water to go but to go to the chloride and deactivate it. But if you put water in acetate, you can form acetic acid, which also has hydrogen bond donors and acceptors, but it tends to tie up less of the hydrogen bonding, accepting, and donating ability because it's in that equilibrium between the acetate and the acetic acid. So you could probably do a calculation, which I haven't done, and show, maybe even model what the water content is. But you can certainly put a lot more water in the acetate than you can in the chloride. Back here and then over here.
So when use it for pulping, what is the quality of the cellulose you get after adding liquid compared to the conventional extraction?
That's a great question, and it has to do with, have y'all ever studied what's happening to the cellulose in solution? Because the things I say, don't take them the wrong way, because a lot of times I'm just kidding. But I never wanted to deconstruct the cellulose. My goal was always to get the highest molecular weight cellulose out I could. And I look at what y'all are doing and say, wait a second, y'all are trying to like cut it down and you want it to be cut. If you control the parameters, the temperature, the time, the acidity, and the type of, because acetate versus chloride, the type of ionic liquid, then you can control the depolymerization. But we have shown that you can put a cellulose of dpx dissolve it, and recover it, and the DP is exactly the same as when it went in. It's a true dissolution. We have shown you can take natural cellulose 1, dissolve it, and only get amorphous or cellulose 2, a true dissolution. We are forgetting in the rush to biofuels what that means. We can take natural polymers of high molecular weight and dissolve them, put them in solution without degrading them, and manipulate them. Now, all the biofuels need to manipulate them and cut them up, and you throw a little acid in with the emim acetate, and it'll certainly facilitate the types of things that you want to do. But it's a different science. Yes. Oh, wait. Okay. I'm going to let you ask a question, but there was one over here that.
How different is the ionic liquid from the DMAC lithium chloride system?
That's an interesting question, and I'd like to talk to you more about that, because one of the things that fascinates me is that people don't know why the cation makes a difference. But if you look at all the cellulose solvents that have worked, including NMNO and DMAC, lithium chloride, then all the cations have approximately the same size, which could be very, very important. Now, how do I see, as an inorganic chemist, how do I see lithium DMAC working? The lithium is coordinated by the DMAC, which means the chloride has no hydrogen bond donors, and so it's essentially also free chloride. But the concentration or the amount of lithium that you can get in there is only like 10%, whereas the ionic liquid is pure chloride. So you can get higher concentrations.
It's a very good solvent for chitin.
It's what?
It's a very good solvent for chitin.
Yep. And also, if you want to dissolve chitin or cellulose, you can also use the naked fluoride if you want to do that. But there's also the practicality of trying to make a commercial process. Lithium chloride DMAC has been around around time, but the corrosivity of that has prevented its use in a lot of big-scale type experiments. NMNO is actually makes a fiber. Y'all probably aware of that, the lyocell process. But lensing took 40 years almost to develop that fiber. They had to overcome the explosion properties. And do you know what the biggest problem with lyocell was that kept it so long from being commercial?
The right water content.
The recycle. The recycle was the commercially enabling feature. They have to recycle 99.99% of the NMNO to make that process viable, even though it's such an expensive fiber. And that's when they went commercial on that. Now, you were very patient.
Your slide just came down from the screen, but I was wondering if you can talk about how that chemistry is different in an ionic liquid versus a water system, or is the system that you're talking about an ionic liquid and water system?
I purposely took out that slide so I wouldn't have to talk in detail about that chemistry. But it is a little bit, there's no water, essentially no water in there in the way that we do this experiment. But it is that reaction at the benzyl ether, that radical mechanism that goes into the quinone. And we have not investigated how that works in an ionic liquid, so all of our knowledge that we're using is based upon what's known for the aqueous system.
Is it reasonable to assume that that kind of chemistry would be happening on other sites in the liquid too? Like, does that change the molecular weight of the liquid?
I think that we were hypothesizing that the most reactive site would be that benzyl ether from all the literature that we had read. But if that radical mechanism just keeps going and we don't stop it, then we're going to degrade the lignin. And it's pretty obvious from the results that we degraded it more than we wanted to. But we did stop it before it went too far, or at least before it went all the way. That chemistry is something that we would like to investigate. I'd be happy to collaborate with y'all, for example. You got lots of people working on this stuff. Anybody else?
So you mentioned the loss of carbohydrates, but do you have a proportion of how much of hemicellulose or how much of cellulose you lost?
Typically, this is a great question as well, and you can see that we haven't gotten as far as we would like in the analytics or in the separation. So I try to use the word carbohydrate rather than cellulose. However, and I skipped through it too fast because I was in a hurry at the end, but we have done some work with the bagasse where we pre-treat it with sodium hydroxide and remove the hemicellulose, and then we get a very high cellulose content. So we're up to about 90% of the available cellulose if we do a pre-treatment to remove the hemicellulose. And we get actually get a much, as you can imagine, get a much better lignin delignification at the same time. But it's an extra step. Nobody wants to hear about it. It's like pre-treated with sodium hydroxide and then dissolved in the ionic liquid. It's not a bad way to go if you can afford the extra chemical demand.
But along with that, you also remove some lignin content.
Yes, that's another good point, of course, yes. The lignin is covalently bound to a lot of the hemicellulose. You do delignify as well, a little bit. But it's actually, you actually get a much better product. Just the pre-treatment itself is not enough, or everybody would do it. But if you pre-treat it, you open it up, you remove a lot of that that's mobile and ready to go, then dissolve it, you actually get a good product.
I'm sure you're familiar with the paper where it talks about the reactivity of ionic liquids, particularly the acetate cellulose.
Yep.
Forming a covalent bond with the using it.
It is acetate after all. So.
We've found in our work, and more support, that we also see compounds formed that appear to be compounds with the ionic liquid.
Yep.
Solvent properties have changed in the ionic liquid. We're looking at how to recover that. Is that something that your group is working on? Is that in that work you'd like to share with us?
There are some things that I can't talk about yet, but you know, if you understand and look at the chemistry, this whole carbene precursor field, which hates ionic liquids because they think we ignored them, which we didn't, then you'll understand the similarity between the N-heterocyclic carbene precursors and ionic liquids, and that can explain a lot of the reactivity, especially when you start looking at acetate and the basicity of that particular anion. However, some of these papers that we keep getting crucified with when we submit our papers for just trying to talk about the science are only in certain situations. The one paper I was told, you have to cite this paper where they said emim acetate will acetylate cellulose. And I wrote back and I said, did you read that paper? Ask the referee, did he read that paper? Did he read the conditions? Do my conditions look anything like the conditions? Did he read the NMRs and every study we did to show that that wasn't happening? It's not a generic effect. It's another case where, oh my God, the ionic liquids are going to react. Well, of course they're going to react if you use conditions where we know that particular type of ion or cation or anion is going to react. It's science. We utilize the science to try and understand the systems. Don't let those people get you down. This PALM stuff is submitted to ChemSusChem, and I think it's going to be accepted, but one referee said, this is nowhere as good as peroxide, and the author should study peroxide in their system and all this. And how do you get across to somebody who has a certain preconceived mindset that while we compare to pulp, we're dissolving everything? We're not doing the peroxide studies, and the PALM studies in aqueous solution are all done on craft pulp after they've been treated with all those chemicals, and you got a cellulose-rich pulp that's maybe already down to 30% lignin. Then you use the PALM. And here we're coming in and say, we use the PALM, and we get much lower than that from the biomass, not from the pulp. And that's the key. I've just tried to emphasize to all of y'all today, it's the science that's important. Your goals are great, but the understanding that you're generating should be driven by what you know about the science.
I was just wondering if you have any idea what the redox potential of that oxidized PALM is and how that compares to some of the enzymatic things.
You're asking me about the PALM again, the redox potentials? No, I can't answer that. So, I'm sorry. I wish I could. If you want a postdoc, you know, we can work on that. No, these are all great questions, really. But you know, palm may not be the answer. Y'all are working with some great catalysts. Maybe those are the answer to what we're trying to do. But you would have to buy into the goal that I have, which is different than the goal that you have.
Let's go ahead and thank Professor Rogers once again.